So again, it's called optimization. Optimization. I can't spell very well today. And optimization is going to involve calculus if there's a function involved. There is also optimization in linear algebra. And in linear algebra, it's a completely different point of view. And it's stuff that you actually did perhaps in pre-calculus. And that's optimization involving inequalities. That's saying that I have, this amount of money to spend on a project and this number of hours that my workers can work, and I have this many hours of machine time that I can use up, and I have this many days that I have to complete the job. You have a whole series of inequalities. What scenario will maximize your revenues given all of these inequalities? That's not a calculus problem. That's a linear algebra problem that we discuss in Math 254. So if I put those types of problems together with the ones we're going to look at, we're going to pretty much have everything covered. And then we come back to do this in 3 dimensions. What's interesting today, my lecture later on today in Calc 3, the first 30 minutes of today's Calc 3 lecture will be a repeat of what I'm about to do to you guys, and then extended into 3 dimensions. It's kind of cool. So they're at the exact same place in their course. They're going to be doing optimization, but with multiple variables. So let's start with a really simple idea. I have a rectangle. Okay. I have a rectangle, let's say with perimeter P feet. So simplest case, I'm going to build a dog run in my backyard, right? An enclosure, and maybe I have 100 feet of fencing. I have 50 feet of fencing. I have 20 feet of fencing. However many feet of fencing you have, that's what the P would be. P would be the amount of fencing required to enclose something. I want it to be rectangular because if I made it some other shape, circular, triangular, whatever, it might be a little bit harder to construct. So here's the idea. I have a set amount of fencing, P feet of fencing. And if it helps you, just put in a number for P. But it doesn't matter what the value of P is. It won't change our final answer. What I want to do is build an enclosure that has the most area possible. So if I had 100 feet of fencing, I guess technically I could have 2 pieces of 50-foot fence laid against each other. So I'd have 50 long, but no wide. And so there wouldn't be any area there, obviously. I could have it, be a foot wide and then 49 feet in the other direction. There's an infinite number of combinations that I could do, but we want to mathematically maximize the area. So I want to talk about how to set up the problem. What's the language we use? So here's what I want to do. I know that the area is simply X times Y. So our goal is to maximize area, which equals XY, subject to. Now, this is called a constraint that I'm going to do. You don't always have constraints, but most of the time with optimization, you will have a constraint. Okay, so there's a limit to how much you can do of something, right? And so in this case, my constraint is the fact that I have exactly P feet of fencing. I don't have unlimited fencing. Oh, so if I had an unlimited amount of fence, just make your rectangle infinity by infinity. That's probably not very realistic. So my constraint is that my perimeter is P. So what's the perimeter of a rectangle? It would be X plus Y plus Y, or 2X plus 2Y has to equal P, which is a constant. Now, I need to maximize this product subject to this. This is not an equation, okay? This is an identity. I'm giving you a specific value. So I'm going to have to take a derivative somewhere along the line, and the derivative is going to be of area because I want to maximize area, but I have 2 variables. I have this constraint and I have 2 variables. Does anybody have an idea that I can make this problem easier on myself? I have 2 variables and I can't do a derivative with 2 variables. I have a function, in other words, of X times Y, but I also have this constraint. Anybody got a bright idea? I could maybe make it a 1 variable problem.
You have to do an implicit.
Substitute. Oh.
Do you have to do implicit derivation or no?
No, not implicit. How can I use it?
substitution for one of the variables?
Beautiful, beautiful. Solve for one of these variables and then substitute it into here. Again, if it helps you think of P as 100, solve for one of the two variables. When I substitute it into here, then area will be a function of only one variable. Now I can take a derivative. So you say, could I do it implicitly? Well, the problem is area right now is a function of two variables, so I would have too much information there. So it doesn't matter which one we solve for. Let's say we want to solve for the y. So I'd have 2y equals p minus 2x. So y would be half p minus x. Okay. Now I can say area is a function of x is x times 1/2 p minus x. Okay, well, I have to take a derivative, so I'd rather distribute. Now 1/2 p is just a number. So that's 1/2 px minus x squared. Okay, now that looks kind of scary, but remember, that's just a number x minus x squared. There's nothing complicated about that. So now, on the last quiz, you did what's called an extreme value theorem problem. I gave you a closed interval and I said, what is the absolute maximum and absolute minimum over that closed interval? So the extreme value theorem says we are guaranteed an absolute maximum minimum as long as I am differentiable over that interval, right? So I have to be able to take the derivative, and that was a fairly easy one. And the maximums and minimums could only occur at critical numbers or endpoints, no other values. So some of you were checking values that were neither critical numbers nor endpoints. If you're going to check even one value that's not a critical number or endpoint, then actually that technically means you have to check all real numbers, because there's no such thing as I'm just going to randomly choose numbers. No, you either check exactly from one group of numbers or you check all reals. Checking all reals might take a little while because there's a lot of real numbers. So maybe that wasn't a good idea. So in this case here, what is the domain? What are the possible values of x? Well, let's see. I said it before. Since we have x in here, I don't need x and y, I just need x. I have p feet of fencing. Well, what if I made half of the fencing here and the other half of the fencing here? Then I could technically put those right on top of each other. What if I made all of the fencing y and I did it that way? So I think it's safe to say in my example here that x has to be between 0 and 1/2 p. Because I could use half the perimeter on x and the other half on the other side, or I could use half the perimeter on y and the other half on the other side. Now, that would be a lousy fence because it wouldn't have any area, but it's legal. I'm not violating any laws of physics. And here's the reason I really want inequalities with or equals, because now that makes it a closed interval. And if that's a closed interval, I can actually use extreme value theorem. So I'm going to show you the different ways that we can finish the problem. So let's do a prime of x, dA dx. That would be 1/2 p, that's a number, minus 2x. I'm going to set that equal to 0, which means that 1/2 p equals 2x, or x equals 1/4 p. 1/4 p. Now, there's exactly 3 ways that I can check this answer. There's exactly 3 ways. I can use the first derivative test, the second derivative test, or the extreme value theorem. All 3 methods absolutely have to produce the same result. It would be impossible to get different results. So I'm going to use all 3 to demonstrate how it looks. You would never use more than one. You just say, which one do I think is easiest in this problem? So let me erase this. I don't need this for the problem. So the first one, let's do first derivative test. So first derivative test means I have a number line. Okay, it would be the a prime number line. Now, what numbers must go on the a prime number line? Well, because it's a closed interval, I actually need the 0 and the 1/2 p, because there's nothing on the other sides of them. I have one critical value, 1/4 p. So right now I've created a situation where there's only 2 intervals. There's the interval from 0 to 1/4 p. There's the interval from 1/4 p to 1/2 p, because there's nothing on that side. There's nothing on that side. Now let's go to our derivative. If I pick a value between 0 and 1/4 p, so think really small, if I pick really small, then that would be positive 1/2 p minus a really small number. That should also be positive. So I'd be here. Okay, now let's pick a value really close. Where are we there? Excuse me. Oh, you know what? I'm sorry. I just looked at this. I'm looking at the, I want to put it in here. Sorry, let's try that again. I put it in the wrong place. I got to put it in the derivative. So if I take a value really close to 0, 1/2 p minus 2 times that number, yes, that is definitely positive. Now let's pick a value that's really close to 1/2 p. Oh, if I pick a value really close to 1/2 p, then this is going to be closer to p, and I'd have a 1/2 p minus close to p. That's going to be negative. This says I was increasing horizontal tangent, decreasing. That means, that a of 1/4 p is the maximum. And it would be an absolute maximum because I'm going up, I turn around and I come down. Basically, this is a downwards opening parabola, in other words. So the first derivative test says I will maximize my area if I use 1/4 p for my x value. Okay, that's the first derivative test. Now let's do the second derivative test. Some of this stuff here. Now the second derivative test says I'm going to take the second derivative and evaluate the second derivative at the critical number. So what is the second derivative? If this is the first derivative, then the second derivative is just -2. So the second derivative, when I evaluate it at 1/4 p, of course, would still be -2, which is less than 0. And as we saw, the second derivative tells me the concavity. If the second derivative is positive, it means I'm concave up. If the second derivative is negative, it means I'm concave down. I am concave down at a critical value. Or another way of thinking about it, I'm concave down where I have a horizontal tangent. Concave down where there's a horizontal tangent means it's a maximum. Concave up at a horizontal tangent would mean it's a minimum. So this means a of 1/4 p, again, sorry, let me make that a little bit clearer. Therefore, a of 1/4 p is the max. Okay, well, obviously it's the same result as the previous one. Now, the last one we're going to try is the extreme value theorem. The extreme value theorem says basically I check the endpoints and I check the critical number in the interval. That's it. So I have to check 3 values in this case. I have to check the endpoints 0 and 1/2 p, and I check 1/4 p. Whichever one yields the largest number wins. And I check those in the actual area function. Now remember, what is the area of x? Area of x was, excuse me, it was x times 1/2 p minus x. This is the actual area. So if I evaluate this at 0, I'd get 0. If I evaluate this at 1/2 p, which was the other endpoint of my interval, I also get 0. And if I evaluate this at 1/4 p, I get a 1/4 p. A 1/2 p minus a 1/4 p is also a 1/4 p, so that would be a 1/4 p squared, if you will, which clearly would be the maximum because I'm comparing it to zeros. Beautiful. If you thought graphically, this is a downwards opening parabola and so on. So all 3 of these tell me that 1/4 p for x would maximize my area. So going back, I had area, excuse me, I had perimeter p, and it said if x is a 1/4 p, now what was y? Oh, y was what? A 1/2 p minus a 1/4 p. Oh my gosh, what have we just proved? that if I have a rectangle with a given perimeter, the maximum area will occur when it is a square. I think that was kind of a no-brainer. I think we all suspected that was coming. We just proved that the rectangle with maximum area given the perimeter would be a square. And in fact, a square where every side was exactly 1/4 of the perimeter. So that makes perfect sense. If I had given you a numerical value, then you would have just come up with that number. But the idea is, how do I prove something like that mathematically? We used optimization. Now, I like using geometry type problems at first because they're fairly easy to understand. Okay, it's not always this simple, by the way. This one worked out nicely because we all had a good feeling of what it would be. So let's do one a little bit higher level. All right. I want to find, all right, let's say it this way. Find the dimensions of the rectangle of maximum area bounded in the first quadrant by the X and Y axes and Y equals, let's say, how about X minus 4 quantity squared? So what the heck does that look like? Okay. Looks something like this. Ah, check it out. So this parabola obviously intersects the y-axis. In fact, I have an x-intercept here. This point here would be 4, 0. And when x is 0, this point here would be 0, 16. I want to draw a rectangle that's bounded by the x and y axes. That means 2 of the sides have to be on the x-axis and on the y-axis. But now I'm bounded by this parabola. So I could be here, I could be here. So let me draw. I could be that. I could be that. There's an infinite number of possibilities. I want the one that's the largest. Now, in this case, it's very unlikely my answer is going to be a square because that parabola kind of throws a monkey wrench into it. So here's what we need to do. Let's call the point of intersection, how about x, y? If the point of intersection is x, y, then clearly that side would be x and that side would be y. So I want to, once again, maximize area, which equals x times y, subject to y equals x minus 4 quantity squared. Okay, I am bound by this thing here. Well, now it's a little easier than the last problem because I clearly would replace this y with this one. Okay, no way around that. That's all I got to do. Now, do I have any constraints on x? Yes, I do. Can x be bigger than 4? Anybody? Can x be bigger than 4?
No.
No, because if I'm over here, then I no longer have the y-axis as a boundary, do I? I'd be on the other side. Can x be negative?
No.
Because again, I'm bounded by the y-axis. So what are my constraints on x? Anybody want to try?
0 to 4.
Gotta be 0 to 4, open or closed?
Close. Open. Oh, I can't think.
Closed.
Technically, it's closed. Now, it'd be kind of boring if I went all the way to 4 because you'd say, well, I'm gonna have 0 area. But like I said before, it doesn't violate any laws of physics. I'm not dividing by 0 or taking a square root of a negative or anything weird. Whenever you can create a scenario where your interval is closed, You always want a closed interval if you can have one, because again, you can use extreme value theorem. Now, in the previous example, I showed you first derivative test, second derivative test, extreme value theorem. The most complicated of the three was definitely the first derivative test. A simple rule of thumb that most people use is, if given the choice, should I use the first derivative test or the second derivative test? If your derivatives are getting easier as you go, like polynomials, use the second derivative test. It's going to be easier algebra. If you have a closed interval, though, often it's the extreme value theorem, because you're not actually looking at any derivatives at that point. You're just plugging numbers into your function. So in this case here, clearly, I can write it like this. X is an element of that is the same as saying 0 is less than or equal to X. This statement and this statement are the exact same thing. This is the more formal, just to remind myself I have a closed interval, but as long as I'm putting or equals, I'm good. So what I need to do now is say area as a function of X is X times X minus 4 quantity squared. Now I need to take the derivative of that. Now I can do that using product rule, or I can just simply multiply that out. So if I multiply that out, that's X squared times X minus 8X, so minus 8X squared, plus 16, so plus 16X. Okay, so if I did this correctly, that's what it should look like. Okay, hopefully I did this correctly. What is a prime of X? Well, that would be 3X squared minus 16X plus 16. Okay, 3X squared minus 16X plus 16. Now that's not the friendliest looking thing, but can I solve that equation if I set this equal to 0? Yeah, I mean, maybe you can factor it. If you're really good at factoring, okay, maybe you can factor it. I'm pretty sure this does factor. In fact, how would this factor in this case? Anybody want to try this one? Pretty sure it does factor though. Like, I don't know, how would it factor? Well, how about if I just
4 times 4.
How about if I just do that? And by the way, if all else fails, some of you, by the way, on the most recent quiz, you got to that bonus problem and you had the icky quadratic that had a coefficient that was not a 1. And you said, I don't know what to do from here. I said, but you can always use your quadratic formula to figure out the roots. That's always legal, because remember, all you're doing is setting this equal to 0. If I can't factor this, I just use my quadratic formula, because the whole point is, if this equals 0, what are my roots? My roots are 4/3 or 4. If I use the quadratic formula, I'm going to still get those things, but I'll probably get it sooner than if I try to factor it. If you're not good at factoring, just go straight to quadratic formula. Now, awesome. And both of those are legal. Now I got 2 critical values though. Wonder how we interpret that now. I'm going to go ahead and erase this. So we can use extreme value theorem. We can use second derivative test. We can use first derivative test. But first derivative test, again, I have to create the number line. I have to do the intervals of increasing and decreasing. All of that's legal, but that's probably the most amount of work. So what if we do second derivative test? So that means I'm going to take the second derivative. Okay, what is a double prime? A double prime of X is 6X minus 16. I am not setting that equal to 0. I am not interested in finding an inflection point or anything like that. You know, that's something else. So what am I going to do with that? Well, I'm going to take these values and I'm going to substitute them in. Okay, so a double prime of 4/3 is, and a double prime of 4 is. So a double prime of 4/3 would be, what's that? 8 minus 16, that's -8. All I care about is less than 0. A double prime of 4 would be 8, which is greater than 0. All right. So what does that mean? Concave down, concave up. if I do the extreme value theorem, let's see. Let me do that one. If I did extreme value theorem, then I'd be saying A of 4. Well, by the way, what's A of 4? 0. If I said A of 0, 0. If I said A of 4/3, well, that would be what? 4/3 times 4/3 minus 4. What's 4/3 minus 4? That would be -8/3, but I'm squaring it. So 64/9. So 256/27. That's going to be my maximum area. Okay. So if everyone looking at that, going, oh, okay. Now, the maximum area is going to come when? Let me erase this. Let's do this. So 4/3 probably about there. There we go. So my maximum area is going to come when X is 4/3, and then Y would be, again, what's the value here? We said 4/3 minus 4 quantity squared, that'd be 64/9. So that's the dimensions of my rectangle that maximizes the area. Okay, kind of a neat thing there, kind of a neat thing. Now, so rather so complicated. If I tried to trial and error this and just guess values of X, well, first of all, what's the chances you were going to guess 4/3? I mean, that would not have been a realistic guess. Now, hold on one second. I'm going to grab something here. Okay. On the schedule, I forgot to mention this last week, but I switching the order of the optimization and the second derivative test because I wanted to give everybody a little bit more time. Optimization, I hate to use the words hard, but most folks say that's the most challenging thing. Let's leave it like that. The most challenging thing we do, maybe even in the whole first semester of calculus. So I wanted to make it as long a period of time, okay, that humanly possible. The quiz on optimization, by the way, it's not due until after. It's not due until after spring break. So that's going to give you a ridiculous amount of time. But I'm flip-flopping the order of the lectures because nothing in the other one, it's not really that critical in terms of the order. But I wanted to give more time. And the other thing is, I've already posted the practice test. Hopefully you notice there's only one lecture after we come back. Okay, that'll be on the next exam. So I believe the next exam is going to have 8 lectures on it. We will finish the 7th lecture this week. So that actually gives us an absurd amount of time to prepare for the next exam, knowing there's only one additional piece of information, and that additional lecture is actually very different from everything else. So all of the stuff in the first 7 won't have any effect on the 8th lecture. So you can really walk out of the spring break saying, okay, I am ready to take an exam now, knowing you still have a couple of weeks, so it's a really good way to prep. Now, we've looked at a couple of simple geometric, well, simple is relative, but now I want to do a different geometric one. This is one of my personal favorites. All right. Now, for many years, okay, I had kids in elementary school, and for many years, I would do the parent helper thing. I would, volunteer for the day. My kids went to a private school, so, it'd help on the tuition if I volunteer. Every parent would do this, like 5 to 10 times a year, each kid, each class. But I remember doing something very specific when I was working with the little kids, and it was to construct things. And so the teacher would always have me cut things out. I'm really bad with a pair of scissors, but I'm going to show you something here. Grab my scissors. Grab a piece of paper. All right. So the problem was this. You have a piece of paper, and it was usually some big piece of, the stiff, whoa, that was weird. The stiff construction paper. And what we're going to do is we're going to make a box. We're going to make a box without a top, an open box from this piece of paper. It's like, how do you make a box from a piece of paper? Well, I learned this in kindergarten. See, what you do is you cut out a corner. You cut out the corner. You cut out corner. You cut out. So I'm taking you all the way back to elementary school. Now, what do you do with this? Now you fold. So what I'm going to do is fold along the cuts. Okay, so I've got my piece of paper and now I've folded it along the cuts. And I have just created, oh, is that incredible or what? You'd need tape at this point, of course. I've created an open box. Okay, everybody got that? Beautiful. So given a particular size piece of paper, here's our goal. I want to construct the open box that has the largest volume. So when I would try to teach these to the kindergartners, how to maximize the volume of their open box, because some of them would cut their squares way too big, some way too small. It's like, no, that box is not going to have maximum volume. You want a box. So, when I tried to show the calculus to the 5-year-olds, it didn't always work so well. But you guys know how to do this. So here's the goal. I'm giving you basically a piece of paper. Let's keep it simple. Let's say it's 30 inches by 15 inches. That would be a typical size. And what I want to do is cut corners. Literally, cut corners. Now, for this to be a box, okay, that was terrible. My corners kind of all have to be the same size, don't they? Otherwise, it really won't fold particularly well. So I've got 4 corners. I'm going to cut the corners. Now, when I cut the corners, the box itself, this is going to be the base of the box. Again, when I cut the corners, I've cut the corners and then I folded. So you can see, oh, where I folded, okay, that's the base of the box. So I've got the base, the height. Well, no, that's the 2-dimensional. The fold here will be the height of the box. So if I said, let's call that X, I don't know how much I'm cutting. Our goal here is to find the value of X that maximizes the volume of my open box. And the reason it's an open box is because I would need another piece of paper if I was going to make it a closed box. That really doesn't. And the closed doesn't affect the volume. So what are going to be the dimensions of this new box? Well, if I'm cutting away X at each end, then won't this be 30 minus 2X? Everybody see that? And same thing here, if I'm cutting X at each end, then this should be 15 minus 2X. So the usable length here is 30 minus 2X. The usable length here is 15 minus 2X. And so the volume of my box, which will be purely a function of X, will be this times this times the height, which would be the X. Now, any questions so far? This is exactly the volume of the box for any value of X that I choose. Now, can X be anything? What do you think? Can X be any number?
No, it'd have to be relatively small, or it would compare to the size.
Can X be negative? No.
No.
I could choose. I don't want to waste paper. I want my X to be 0. It's not a very interesting box, but technically X could be 0. Is there a maximum value X can be? Can I make the cut so big that there's no more box? What's the biggest X could possibly be?
7. No more than half.
I think you're both right. What, one at a time?
No more than half.
No more half of what?
Then the length.
Which one?
The shorter one, the smaller one.
The shorter one. So 7.5 or 15 halves. Does everybody agree? Oh, so if I cut it, if I had cut it 7.5, then there's no more box basically. So I'll say 15 halves or 7.5. So X is definitely a closed interval. I can choose not to cut it. I can choose to cut it all the way till there's nothing left on that side. In other words, I'd have 0. Now, I need to multiply this out. I could use product rule, but I don't want to use the product rule with three things. That'd be nasty. So bring this down. This is going to be 30 times 15. So that's 450x minus 30 minus 60. So that'd be minus 90 and then x squared plus 4x cubed. So this is the volume of my box for any x in this interval. Now notice if x exceeded that interval, if I was on the other side or if I was negative, that would actually give you a negative value for the volume, which I think we agree. Volume probably shouldn't be negative. Yeah, that would be bad. So now v prime of x is 450 minus 180x plus 12x squared. Okay. Now from there, I need to know basically when is this zero? Now I can factor it, but it's doubtful that I'm going to get rational numbers. Okay. Probably going to get irrational. So trying to factor it might be a waste of time anyway. So let's go straight to quadratic formula. So x is 180 plus or minus the square of 180 minus 4 times 450 times 12 all over 2 times 12. All right, so let me get out my calculator. You don't need to do that in your head, but you do need to do that. So 180 squared minus 4 times 12. Okay, so is that right? Make sure we don't have any boo-boos there. Minus 90. Yes, okay, that looks good to me. So I've got 10,800. This is root 10,800. Now I'm thinking root 10,800 might have some pretty humongous perfect squares in it. Yep, in fact, that's 60 root 3. How nice. Okay. Now I do clearly get two answers. So 180 over 12, that's 15. 60 over 12, that's 5. So I get, if I didn't mess this up entirely, again, I'm sorry, that's not 12.
Times 2.
Sorry, that's not 12, that's what? That's 24. Sorry about that. Now, just make sure everything else there looks beautiful. Okay. So when I do this, that's going to be 15 halves. Plus or minus 5 halves root 3. Now I got two roots and I'm pretty sure they're both positive, but are they both going to be answers? Or is it pretty obvious that one of them can't be an answer? It should be obvious that one of them can't be an answer. Didn't we say x had to be between 0 and 15 halves? Our roots are 15 halves plus or minus. Which one should we throw out? The plus or the minus?
Plus.
The plus, because if 15 halves is our upper limit and I take 15 halves plus, that would be outside the values. That's why identifying the domain is so critical. I might proceed in this problem and use a value that's technically impossible. Yikes. So it's going to be the only critical value we're going to be able to use is the 5 halves minus. Okay, that's it. Now, the nice thing is I can use extreme value theorem in this case, and I can go light speed. And here's why. If I do extreme value theorem, I'm going to check my endpoints, which, by the way, will both be 0. Why? If I use an x of 0, I get 0. If I use an x of 15 halves, I get 0. And then the last one would be whatever this is. And we can convert that to a decimal soon enough. All right. So if I use that, what is that number? That's 15. It's about 3.17. This is about 3.17 approximately. So if I use that value in here, this is definitely going to be positive. And I'm just going to leave it like that. I'm going to say this is positive. I don't really care what the value is yet. I wanted the dimensions. So I'm going to get a positive number. That means I know this is going to be the maximum. The extreme value theorem, I checked the endpoints and the one critical number and I won. The nice thing is about these types of problems is that when you have closed intervals, it is often the case, not always, it is often the case that the endpoints of your interval produce zeros, like they did in this case and in the last case. Now, I said I wanted the dimensions of the box. I'm sorry, not the dimension, I'm sorry, the dimensions of the cut. So that means my cut's going to be about 3.17 inches in each direction. So what are the dimensions of the box as a result? Well, 30 minus 2 times 15 halves minus 5 halves root 3. So if I multiply that out, that'll give me 15. And then over here, plus 5 root 3. That's my long side. And how big is that? Again, don't use the calculator until you actually have to use the calculator. So that's, oops, try that again. 15 plus 5 root 3. It's about 23.66 inches. That would be this side. That's how big it is. And then over here, the other side would be 15 minus 2x. Well, that's 0. So this would just be 5 root 3. And 5 root 3 is about 8.66 inches. So my box is going to be basically this long, this wide, this tall. Okay. Now it's kind of crazy. I don't know that I could construct a problem like this where we got an integer answer. That's just not going to happen. In real life, you don't get integer answers to all questions. In fact, it's highly unusual that you get integer answers. So this case here, this was a bit more beefy. Now, again, if I'm using the extreme value theorem because I have a closed interval, that's always the best case scenario. Now we're going to do the biggest problem of the day. And I just keep wanting to show you different looks of things. And we're not done. We have several more types of problems we're going to look at. And I'm going to give you some very specific examples where this is used in real life, by the way. Okay. All right, so here's the situation. All right. You are here. Okay, this is supposed to be water. Sorry, that was just bad. Okay. There's a body of water here. Maybe it's a lake. I don't know. And on the other side of the body of water, there's a pub. Okay. If I go straight across, that's 3,000 feet across. If I'm going this direction, it's 5,000 feet. If I said, if I'm going, think of this like a box, like a right angle, okay? Now, it's a body of water. So I'll use William because he's an athlete. So William's just put in a hard day of work over here. The pub is over there. You need to get to the pub. And you don't want to take your time. You want to get there as fast as possible. So here's a situation where I want to minimize the time, but here's the problem. You're going to have to swim some, you're going to have to run some. Now, I was actually looking it up online because I always like to use numbers that are real. So you didn't know this, but William is first cousins with Michael Phelps. So he is a tremendously fast swimmer and can actually swim 8 feet per second. That doesn't sound very fast, but that would be actually world record sprinter speed kind of speed. And I looked at, if you're running about a 5-minute mile, which is, pretty good running, you're going to run about 17 feet per second. Okay. Those are both very, very fast speeds. You're a triathlete at this point. So the question is, does he swim straight across and then run the whole way? Or does he swim the whole way and run none? Or do you go partially across and then run the rest of the way? Those are my 3 possibilities. Well, since I don't know how long any of these are going to take and I don't know what's the fastest, here's the safest way to set this up. We're going to swim to a point, an arbitrary point right there. And let's say that arbitrary point is X feet from the straight across. Now, the one thing you're not going to go that way. That doesn't make any sense. If you're swimming straight across, that's the shortest distance, or you're swimming some other way. Now, here's the thing. We're going to set up a problem and we're going to minimize the time. It might turn out that X is 0. If X is 0, that means I'm swimming straight across. It might turn out that X is 5,000. That meant I swam the whole way. Or it might turn out that X is some number in between. So we're going to set it up like this, and then we're going to let the calculus dictate what X is going to have to be. But clearly, X is going to be between 0 and 5,000 because it's 5,000 all the way across. So again, I can swim straight across, in which case X is 0. Okay, that means I'm going to run 5,000. I could swim all the way across, in which case X is 5,000 and I would run 0, or I'm going to swim to some point in between. Okay, that's how it works. Well, how far am I swimming then? Well, that's the hypotenuse of a right triangle. So that would be X squared plus 3,000 squared under the square root. Okay. Now we know that distance equals rate times time. Let's remind ourselves. If distance equals rate times time, then time equals distance over rate. And I want the time it takes. So the time to swim would be how far I swim over the rate that I swim. So it would be the square root of X squared plus the square of 3,000. I'm just going to leave it like that over 8. The time to run is how far do I run? Now, how far are you going to run? You're going to run, if you're swimming to some arbitrary point, you're going to run 5,000 minus X, and that number can be anywhere from 0 to 5,000. But this is how far you're going to run. You're not running here, you're running here. So that would be 5,000 minus X over 17. So now I'll call my function time. Time as a function of X, because how long it takes is clearly depending on what the value of X is. It's going to be this plus this. I'm just simply going to add up those two quantities. So I'm going to rewrite that as 1/8 times X squared plus 3,000 squared to the 1/2 power. I have to take a derivative. It's easier to write it like that. Plus 1/17 times 5,000 minus X. So for any value of X, where X ranges between 0 and 5,000, for any value of X, this is exactly how long in seconds it will take me to get to the pub. Or I'm sorry, William to get to the pub. I'm not going to work, that's too far away. I'm going to work over here. All right, so what is T prime of X? That would be 1/16 X squared plus the square of 3,000 to the negative 1/2 times 2X. Over here, this is just 1/17 times negative 1. Oh, that's easy enough. So if I clean this up, this would be X over 8 times the root minus 1/17. And I'm going to set that equal to 0. Okay, so when I set that equal to 0 and I multiply both sides by a common multiple, that will leave me with 17X equals 8 times the root, right? So multiply both sides by 17 and by 8 times the root. So now I need to get the X by itself. The only way I'm going to be able to do that is to square both sides. Okay. So now I've got 289X squared equals 64 times X squared plus the square of 3,000. Okay, so if I distribute, that's 64X squared plus 64. So why don't I just multiply that up? Because someone would be taking a square root at some point. I'm lazy. Okay, when I throw that over, I've got 225x squared equals 64 times the square of 3,000. So x squared is 64 times the square of 3,000 over 225. So x is the square root of this. This is why I didn't square anything. When I take the square root of that, that's just going to be 8 times 3,000. That's 15 squared. Turns out I didn't really need a calculator there. So I think that's going to be 1,600, and that's feet. That is not time, that is distance. So our x turned out to be an integer value. How nice. Now, we don't know if that's the best case, but we know if I land 1,600 feet from the straight across, that means I'm going to actually run then 3,400 feet. And if I replace x with 1,600, then I've got the square root of 1,600 squared plus 3,000 squared. And that turns out to be exactly 3,400. So this scenario says I'm going to swim 3,400 feet. Oh, what do you know? And I'm also going to run 3,400 feet. So does that mean that's my answer? No. That might be the worst case scenario. Oh, you just did a closed interval and you got one critical value. Why would that critical value have to be the best case? It could just as easily have been the worst case. You see, I've got a cubic function. In fact, I don't have cubic. This is worse than a cubic function. This is a square root of a square. Sorry, I have no idea what the graph of this looks like. I just found a critical value, but a critical value could have been at the minimum. It could have been at the maximum. I do not know that. I have to test it. Now, in this case here, I don't want to do a first derivative test. Yikes, not with that. No, I'm going to do extreme value theorem. I'm going to test 0, 5,000, and 1,600. And I'm going to see which gives me the lowest time because I don't know the answer. I really don't know the answer. Let's see, where can I erase? I'll erase here. Okay, since we already have everything right in front of us. So for x equals 0, we have x equal 5,000 and we have x equals 3,400. These are the values we're going to test. So the time is, now this is actually pretty easy. If x is 0, what does that mean? That means I swam exactly 3,000. And so where is that? Right here. Sorry, I swam exactly 3,000. So that would be 3,000 over 8. And it means I ran exactly 5,000. So that would be plus 5,000 over 17. Now, because this is a time, yes, you can give me a simplified fraction. That would be a perfect answer. But I don't think I would recognize the value of that. So at this point here, I'm going to use my calculator. 3,000 over 8. So that means it took me 375 seconds to swim. And then added to that 5,000 over 17. So that's about 669.1, and that's seconds. Sorry, you can't read that. Now, second scenario. I swam the whole way. So that means that I'm going to be 5,000 squared plus 3,000 squared under the root over 8. There was no running. I swam the whole way. Okay. But remember, he's got Michael Phelps speed, so that might not be a bad thing. So square root of 5,000 squared plus 3,000 squared over 8. 728.9 approximately. Okay, so running the whole way and swimming the shortest distance was a little bit faster than swimming the whole way. And then finally, I'll do this in different color. I don't want all this to run together. So now we just said we're going to swim 3,400 we're going to run 3,400. That's coincidental, by the way. That's, it just happened that way. And what does that give us? That gives us exactly 625 seconds. So it turns out that is the best. Awesome. So what is that? That's 10 minutes and 25 seconds. So if I aim at this point right here, and then I run the rest of the way. So here's what's going to happen. So the next day before work, William's going to drive over here. There are street lights all along the way. And so what he's going to do is he's going to break the light bulb of the street light that's right there, so that as the sun starts going down and the street lights come on, when he's getting ready to jump in the water, he's going to swim right to the point below the broken street light. I saw that in a movie once a long time ago. It's a good strategy, It's kind of the Mission Impossible strategy. And he's going to swim to that point and then run the rest of the way. Problem is, this problem took too long, so he's not going to be able to make it today before closing time, but every day in the future, he knows he's got 625 seconds to get there. Now, this was gnarly, but again, it would be impossible to guess at an answer because there's an infinite number of possible answers. Now, before we move on, does anybody have a question? Okay, like, I don't know if I have a question. I have a situation and I simply want to maximize or minimize. That's really what it comes down to. Now, where is this used in general? Well, I'm going to give you a really, really simple example. Airlines and hotels. This is one of the most common type of mathematics, the optimization. Now, think about this for a moment. If an airline just kept raising their price and raising their price, they'd make so much more money on their tickets, but they'd also lose a lot of their passengers. If they keep lowering their price and lowering their price, they'll get all the passengers in the world, but they won't make any money. Hotels, it's the same thing. If I keep lowering the price of my rooms, I'll fill up my hotel, but I might not make any money. And if I keep raising the price, I'll get so much more per room, but I might not have any patrons. So there is a best price to charge. And one of the strange things that a lot of people don't realize when it comes to airlines and hotels, operating at capacity is usually a very bad idea. Because for me to be able to fill up my hotel or my airline, that means I've got to lower the price to a point where I can fill it up. But that's rarely going to be the best case scenario. And it kind of defies logic at first until you realize, oh yeah, for me to fill it up, I might have to keep lowering the price until I might even be losing money. So capacity isn't the goal. The goal is to maximize revenue. Now I'm going to use a hotel as an example because that's one of the easier ones. And so what we're going to do is a few basic assumptions. There's a cost associated. So a hotel room, you're going to get revenue coming in, and then you're going to have the cost. Remember, profit is always the difference between revenue and cost. Hang on a second. If profit's the difference between revenue and cost, but the cost per room is essentially the same, then whatever is required to maximize profit would be the same as required to maximize revenue. So we just say, let's maximize revenue. The idea is, let's say it's a certain amount of money to rent a hotel room, and there's a certain amount of money to clean and maintain that whole hotel room. Well, it's reasonable to say the cost per room is the same, actually, because I have a staff cleaning. I don't get a discount by having more rooms. If I have a cleaning staff, it costs this much for every room. If for basic utilities and things, it's basically the same cost per room. So we want to maximize the revenue. So I want to come up with start with a really simple example, an overly simplified example. But we have found through experience that every time we raise the price, let's say it's our hotel, every time we raise the price, we lose people. And every time we lower the price, we gain people. And you could do this with products on the shelf at the grocery store. When you raise the price, you generally lose sales. And when you lower the price, you generally gain sales. So what is that perfect price to charge? So let's say, okay, a hotel has 1,000 rooms. It's a big hotel, right? 10-story hotel out in Las Vegas, right? Lots of rooms and everything else. So I've got a hotel has 1,000 rooms. Usually, let's say 900 are occupied. Let's keep it real simple, at $120 per room. Okay, so let's say that this is the situation right here. A hotel has 1,000 rooms, usually 900 are occupied. All right. So now we're going to look at the situation. If I raise the price, I expect to lose people. If I lower the price, I expect to gain people. Oh, hang on a second. Hold on 1 second, folks. Let me pause this for just a second. Sorry about that. That was one of those really important ones. I wasn't expecting the call right now. Yeah, kind of fate of the universe, hanging in balance, that sort of thing. So getting back to this problem here, the hotel has 1,000 rooms, usually 900 are occupied. And we have found through experience, let's say, because we've done this before and we've actually interviewed our patrons to say for every, let's say, for every $10 increase or decrease in price, we lose or gain, okay? How about, let's say 25 rooms. Now, what that means is if I raise the price $10 per room, I'm going to lose 25 rooms. If I raise the price $20 per room, we're going to lose 50 rooms. But if I lower the price $10 per room, we're going to gain 25 rooms. If I lower the price $20, we're going to gain 50 rooms. We found this out through experience, let's say. Okay, so the question is, what is the best price to charge to maximize my revenue? Now, revenue is simply the product of how many rooms I have rented times the price I'm getting per room. Okay, so from right now, this point on, this is a fairly simple problem because the things that I'm going to be working with are really simple linear functions. This is a little overly simplified. I mean, in reality, it might not be an absolute even match, but for the sake of argument here, I want to make this as simple as possible because usually this requires what's called mathematical modeling. You have to do a lot of research and figure out exactly, what are the changes going to be for increases and decreases, but we're going to make this really uniform. So let's start by saying, let's let X equal the number of price, we'll keep it simple, increases. So if at the end of the problem, we find that X equals 10, that means we raise the price 10 times. We raise the price $100. That's what it would mean. What if at the end of the problem, X turns out to be negative 10? Oh, well, then that would mean I lowered the price 10 times, or I lowered the price $100. So anything's fair game. So if X is the number of price increases, then we need to put a bound on X. Well, what am I bounded by? I only have 1,000 rooms. So let's think about this. If I'm gaining 25 people every time I drop the price $10, I only have room to gain 100 more people. I can't have more than 1,000 people. So if I did exactly 4 price lowerings, I would gain 4 times 25 or 100 people. So I cannot drop the price more than 4 times, okay? Because if I drop the price more than 4 times, I would be exceeding capacity. Now, I can raise the price all day, but at some point I'm going to scare away all my patrons. So now let's look in the other direction. How many times would I have to raise the price to lose all 900 people? Well, 25 goes into 900 36 times. So if I raise the price 36 times, I will lose all 900 people. And after that, I have to stop because I can't have a negative number of people. Okay. So the range here again, this would mean I'm now at 1,000 rooms. This would mean I'm now at 0 rooms. So that's the range of possible values that I can lower or raise the price. Now, what is the price going to be? Well, it started at 120. And if I raise it X times, that means 10 times X is the dollar amount that I'm raising it. And by the way, what if X turned out to be, 0.7? Well, 0.7 times 10 is $7. Oh, okay. So X technically could be a decimal because I'm multiplying it by $10. So if I raise the price X times, then it's going to be 120 plus 10X. That's exactly how much. So 1 price range, I'd be at 130. 2 price raises, 140, and so on. the number of rooms, well, I'm starting right now with what, 900? And now I'm going to lose 25 rooms for every price increase. And I'm doing X increases, so I'm going to lose 25X rooms. Okay, so hopefully you're all with me on this. Now, by the way, what if I choose to do nothing? Status quo, I just leave it alone. Well, then X would be 0. And I'd still have 120 times $900 per night. Okay, so my revenue as a function of X is simply the product of these two things. Okay, and that will be what, 108. 108,000. Okay, minus, what would that be? 3000X plus 1800X. Can't quite fit this in. Minus 50X squared. Okay, so that would be 108,000 minus 120X minus 50X squared. So if I did this right, it looks like that looks about right. 2,000, 1,800. Okay. All right. So this looks like exactly how much I'm going to get. So if I do nothing, remember, if I do nothing, then that's status quo. Okay. So I need to take a derivative. And if I take a derivative of this, I'm going to get negative 120 minus 100X. Okay. Negative 120 minus 100X. Okay, and let's see. If I set that equal to 0, I'm going to find that's 120 equals negative 100X. So X is negative 1.2. I said X could be a decimal. Is negative 1.2 in our range of values? Yes, it is. So what does this mean if X is price increases? That means I'm going to be decreasing the price. That's what it means. I'm going to decrease the price. In fact, anybody, how much am I going to decrease the price by per room?
$12.
$12. That's it. Yeah, that's what this math tells me. Now, is that the best case scenario? Or is it possible that's the worst case scenario? Ooh, I don't know. I need to test. And how do I test? I go with extreme value theorem. I test the endpoints and I test that value. So I'm going to test -4, +36, and -1.2. This will tell me. Now I need to erase some of this. Okay, so R of -4, R of 36, R of -1.2. Okay, so by the way, the status quo wasn't really a possibility. We're making $108,000 a night in revenue. If we do nothing, that's how much we make. But what we're trying to do is figure out what the optimal price to charge that I have the most revenue on a nightly basis. Okay, so if I said, let's drop the price 4 times, that means my revenue would be 120, excuse me. I'm dropping the price. Hold on a second. Oh, you know what? Oh my goodness. Folks, we have a boo-boo. I just caught it. Nobody caught that, did they? That should have been a 10x. Yikes. Okay, so I'm going to have to erase this. Well, I'm glad I caught that now. That was supposed to be 120 plus 10x. I can't read my own writing. All right, so let me remultiply that together. This doesn't change how we do the problem. This just changes our final result. So that was -3000x plus 9000x minus 50x squared. Okay, that's a little bit different then. So that's plus 6000x minus 50x squared. Okay, now when we take our derivative, Boy, sorry about that. I'm glad I caught it now. I'm just surprised none of you guys caught that. So this would be 6,000 minus 100x, and that's equal to 0 when x is 6. Okay, so x turns out to be positive 6, not negative. So that means we have an extrema. We don't know if it's the best or the worst. Remember, this could be the worst case scenario. This could be I lose money. This could be the absolute bottom of the barrel. All right. So that's supposed to be a 6 then. All right. So when it's -4, it means I dropped the price $40. So that would be 80 times. And I
Wait,
would
shouldn't that be 2,500 x squared? Because it's 10x times 25x for the last.
yeah. Yes, Nate, you are, man. I kept the old number, didn't I?
I thought it was a little funky looking, but I was like, yeah, he probably knows why.
No, yeah, I have the worst view in the house, by the way. I'm tunnel visioned here. So you're right, Nate, that should be what? 500? My math is not good right now, is it? It's minus. So now that's going to be minus.
You need another coffee.
You know, I finished my last espresso like 6:20 this morning. Yeah, that's not good. Let's just make sure. The problem is so simple in setup. I don't want to have wrong numbers. So minus 3,000 plus 9,000 minus 250x squared. Why am I putting 500? That's 250x squared. Yikes. Okay, one more time. So now my derivative is, I think my math was terrible on the last one anyway. So minus 500x. Actually, it's not a 6. I believe that's going to be 12. All right. So this means, man, we're going to be gouging these people, aren't we? We're going to be setting the price through the roof. Yikes. So this is 80 times 100 is, I'm sorry, 80 times 1,000. Sorry, $80,000. Is this good or bad? Well, remember, what was status quo? Status quo was $108,000 a night, $120 a room, 900 rooms. If I drop the price $40 per room, I will now have capacity, but I'm only going to make $80,000. I'm going to lose $28,000 a night over what I'm currently making. That's a terrible idea, isn't it? Okay. Now, this one's worse. If I raise the price 36 times, that means I'm going to be charging $480 a room, and I'm going to rent exactly 0 rooms. So I'm going to have $0. I think that's probably the worst case scenario. Yeah. By the way, I didn't get 0 at both endpoints. So here's a situation where operating at capacity, I'm losing money over the status quo. I don't want capacity. What I have now is pretty good, but now I'm going to look at 12 price raises. If I raise the price 12 times, that means I'm going to raise it $120 a room. That means I'm going to charge $240 a room. That's absurd. I'm also going to lose 300 rooms. Yikes. I'm only going to rent 600 rooms, but that means I'm going to make $144,000, folks, and that's significantly more. Ooh. So it turns out in this particular scenario, charging $240 a room, doubling the price, I'm only going to have 600 rented rooms, but I'm going to make significantly more money. Well, figure. Well, by the way, this is as real life as it gets. Every hotel in America has this kind of decision they have to make. Now, let's just assume that all the rooms are the same price. We know that's not necessarily the case. But if all the rooms are the same price, turns out the gouge factor, I make more money. Yes, I have a lot of empty rooms. So what do I do with those? Priceline, Expedia, Orbitz. You guys ever heard of those sites? When I travel, first thing I do is I type in Expedia and I put the hotel that I'm looking at and I get the cheapest room. See, right now we're now going to gouge people and charge $240 a night. And we're going to only rent 600 rooms. What do we do with the other 400 rooms? We put them on the discount websites and we will rent them out at $120 a night. And when you get that $120 a night room at a $240 a night hotel, you are so stoked. And those last 400 rooms that we just did the Priceline thing, it's pure gravy. I've already maximized my revenue by gouging them at 240. And here's the other thing, by the way, this is not unethical. This is not illegal. The $120 that I'm giving away on the discount website, I can claim as a tax write-off because I'm losing $120 per room by renting them out. You give them to vacation packages, the people, you just want a 3-day, 2-night, whatever. This is what is done. This is why airlines do not operate at capacity in general, because they will lose money. So what do they do when they've filled up 80 or 90% of their seats? They then discount the rest of the seats. So if you fly Southwest, I'll use Southwest for example, because most of my flying is north and south. And so I usually fly on Southwest. I book my flight way ahead of time. It's dirt cheap. As I get closer and closer to the departure date, though, if I haven't bought my ticket, that price is going to go up and up and up and up because they know they got me. They've already maximized their revenue. They do not need to sell those last seats. And so they do just the opposite. They don't discount those last seats. They make those last seats way more expensive because they don't need to rent. They don't need to give them out at all. So in real life, you may have experienced this in many things where you had a product that you bought and then all of a sudden the price just went out of control without any particular reason. That's because the market research that the company did said, you know what, if we raise our price, yes, we will lose customers, but we might actually gain other customers. And by raising the price, we will maximize our revenues. And so in the long run, we're better off. This happens all the time with products in the United States. And I don't want to go into companies, but there are a few very prominent companies. I'll give you, without mentioning names, there was a certain Mick restaurant that all through the 90s and first decade of the 2000s, I know out on like Miramar Road, they had 19-cent hamburgers like 1 day a week. It's just absolutely absurd. And I don't know how you make money on a 19-cent hamburger, but they would do absolutely absurd things like that. And with your Happy Meals, again, I'm not going to mention names of restaurants. And then somewhere 15 years ago or so, they decided, you know what, we need to change our marketing strategy to make it sound like we're a high-end restaurant. And all of a sudden it went from dirt cheap to now competitively expensive with other restaurants without actually changing anything. The most sold beer on planet Earth, not just the United States, in the 1960s, 1970s, 1980s was Budweiser. It was the cheapest beer in the United States. And so somewhere in the 80s, 90s, they decided to change their strategy and start marketing themselves as an elite beer. And then they started charging a lot of money. They lost most of their customers overnight, but gained an entire new set of customers because people are saying, oh, it's expensive, it must be better. They literally doubled their price overnight. Lost one group, got another group, and now are making much more money than they did before. Now, it might feel unethical if you were a customer that got lost, but this is actual strategy based on optimization theory. Somebody had to do the research to come up with a working model that's a little more complicated than what we just did, but a working model that says this models our sales based on the current situation. Now, if we change the price or we change something, what will that do for us? And this is done in real life all the time. Big companies often have optimization specialists working for them. And it's a pretty good job if you can get it because it's all math. So anyway, I wanted to give you some exposure. Now, there's nothing about calculus in this problem that was difficult. Taking a derivative, we're setting it equal to 0, we're solving. But what is it we're doing? What question are we answering? So this is optimization. This is considered the most important application in calculus because it's really the only application that involves money. So it's practical in everyday life. A lot of companies will have either on staff or they will hire somebody called an efficiency expert. You may have heard that term before. I knew somebody who would do this. A company would bring them in, they'd spend 2 weeks, they'd look at everything that company was doing, how they were running their business, and then they would make suggestions to them. If you change this or you change that or you cut here or you cut there, you can maximize your revenues, or in this case, maybe it was minimize their costs. And they had to do a lot of work and create models, but it was all calculus. And in the long run, the company would pay them very well for that because the company was now saving so much money, so much more than the cost of the efficiency expert. So this is out there. It's interesting. This is just exposure, what we just did today. So let me go ahead and stop.